Hi everyone, welcome to this video lecture on Unit 4 Central Forces Part 6. In this video lecture, I would like to explain the motion of satellites and some problems. There are certain heavenly bodies which revolve around the planets. They are called satellites. There are two types of satellites: natural satellites and artificial satellites. Moon is the natural satellite of the Earth. Artificial satellites are put into orbits around the Earth by various countries. To describe the motion of satellites, we have to derive orbital velocity, time period, angular momentum, etc. Orbital velocity of satellites. The orbital velocity V0 of a satellite is defined as the velocity which the satellite must acquire to rotate around the Earth in circular orbit. Let m be the mass and V0 be the velocity with which a satellite revolves around the Earth in an orbit of radius r. In the diagram, this is Earth of mass capital M, this is satellite of mass small m revolving around the Earth in circular orbit of radius r. The centripetal force acting on the satellite due to Earth is F is equal to mv0 square by r. The gravitational force between the Earth and the satellite is given by F is equal to g into capital M into small m by r square. This is according to Newton's universal law of gravitation. The necessary centripetal force can be obtained by gravitational force of attraction between Earth and Sun. Therefore, mv0 square by r is equal to g into capital M into small m by r square. On solving, we get v0 is equal to square root of capital G into capital M by small r, where capital G is universal gravitation constant, capital M is mass of the Earth, and r is radius of the orbit of the satellite. But the accidental gravity G in terms of capital M and capital G is given by small g is equal to gm by r square. That is equation 2. From equations 1 and 2, we get v0 is equal to square root of gr. On substituting the value of g and small r, we get v0 is equal to square root of 9.8 into 6.4 into 10 to the power of 6, that is equal to 8000 meters per second, that is equal to 8 kilometers per second. That is equation 4. That means when the satellite is very close to the Earth, the orbital velocity of the satellite is 8 kilometers per second. Now we have to derive the expression for time period of revolution of satellite around the Earth. Time period means the time taken by the satellite to complete one revolution around the Earth. This is denoted by capital T. Time period T is equal to 2 pi r by v0, that is equal to 2 pi r by square root of gr, that is equal to 2 pi into square root of r by g, that is equation 5. At a height h from the surface of the Earth, the accidental gravity is given by g dash is equal to gm by r plus h whole square. Then the time period t is equal to 2 pi into square root of r plus h by gm by r plus h whole square, that is equal to 2 pi into square root of r plus h whole cube by gm. But g is equal to gm by r square at the surface of the Earth. Therefore, time period t is equal to 2 pi square root of r plus h whole cube by gr square, that is equal to 2 pi into r plus h whole power 3 by 2 by r into square root of g. That is the equation 6. Now we have derived the expression for angular momentum of the satellite. The angular momentum of the satellite L is equal to mv0 into r, that is linear velocity into radius. mv0 is linear velocity of the satellite and r is the radius of the orbit. Therefore L is equal to mv0 into r, that is the equation 7. Now L is equal to mr into gm by small r, that is equal to square root of capital G into capital M into small r into m square, that is constant. Hence the law of conservation of angular momentum holds good in case of a satellite. In this way we can derive the expressions for orbital velocity, time period and angular momentum of the satellites. Now here we have to calculate few problems depending upon Kepler's laws of planetary motion, eccentricity of the planet, angular momentum of the planet, etc. If first problem is, if the earth be one half of its present distance from the sun, what will be the number of days in the year? When the earth revolving around the sun, the time period of the earth is 365 days, that means 1 year. If the distance between the earth is half of the present distance, what will be the time period of the planet? That means what will be the year? According to Kepler's third law, t square is proportional to a cube. Therefore, t1 square by t2 square is equal to a1 cube by a2 cube. Here t1 is 1 year, that means 365 days. a1 is equal to x, suppose a2 is equal to x by 2, then what is the value of t2? Now 365 square by t2 square is equal to x cube by x by 2 whole cube. On solving we get t2 is equal to 129 days. The second problem is, the mean distance of Mars from the sun is 1.524 times the distance of the earth from the sun. Calculate the period of revolution of the Mars around the sun in terms of earth years. According to Kepler's third law, t square is equal to a cube. Therefore t1 square by t2 square is equal to a1 cube by a2 cube. From the data given, t1 is equal to t earth is equal to 1 year, a1 is equal to distance of the earth from the sun, that is x, a2 is equal to distance of the Mars from the sun, that is equal to 1.524x. Then what is the value of t Mars? Now 1 square by t Mars square is equal to x cube by 1.524x whole cube. On solving we get t Mars is equal to 1.88 years. The next problem is, estimate the mass of the sun assuming the orbit of the earth around the sun is a circle. The distance between the sun and the earth is 1.49 into 10 to the power of 11 meters and capital G is equal to 6.67 to the power of minus 11 Newton meter square kilogram per minus 2. Given the radius of the orbit of the earth, that means the distance of the earth from the sun is r is equal to 1.49 into 10 to the power of 11 meters. Time period t is equal to 365 days, that is equal to 365 into 24 into 60 into 60 seconds, and capital G is equal to 6.67 into 10 to the power of minus 11 Newton meter square kilogram per minus 2. Mass of the sun, capital M is equal to 4 pi square r cube by t square into capital G. On substituting and solving we get the mass of the sun, capital M is equal to 1.972 into 10 to the power of 30 kilograms. Now the next problem is, the greatest and least velocities of a certain planet in its orbit around the sun are 30 and 29.2 kilometers per second. Find the eccentricity of the orbit. Since the angular momentum of the planet is constant, mvara is equal to M, Vp, Rp, where M is the mass of the planet, Vp and Rp are the velocity and position of the planet at perigee. Perigee means nearest point from the sun, and Va and Ra are the similar quantities at the apogee. Apogee means farthest point from the sun respectively. Here Ra is equal to R maximum and Rp is equal to R minimum, Va is equal to V minimum and Vp is equal to V maximum. Therefore, eccentricity epsilon is equal to R maximum minus R minimum by R maximum plus R minimum, that is equal to V maximum minus V minimum by V maximum plus V minimum. Therefore, eccentricity epsilon is equal to 30 minus 29.2 by 30 plus 29.2, that is equal to 0.0135. This is nearly 0. Hence, the value of eccentricity indicates that the orbit is very nearly circular. In this way, we can derive and calculate some problems. The differences used to explain the topics from Unit 1 to Unit 5 are B.Sc Physics Volume 1, Telugu Academy, Hyderabad. Unified Physics, that means Mechanics and Properties of Matter by Dr. S.L. Gupta and Sanjeev Gupta, J. Prakash Nath and Co. Merit. Fundamentals of Physics Volume 1 by Resnick, Holiday and Crane, Billy, India, 2007 edition. I am very thankful to those others to use the topics to explain in the video lectures. Thank you.